Okay, so our topic today, we're going to continue where we left off last week with building a custom linked list. If you haven't had a chance yet, I suggest that you take a look at Lab 2 after today's class. Last week and this week will teach you most of the things that you need to know in order to be able to do Lab 2. The one thing that I'm purposely not teaching is the exact algorithm for adding and removing. And that's because I want you to use your creativity and figure it out for yourself. But everything else is contained within these 2 weeks worth of classes. And maybe a tiny bit from next week. But next week's stuff isn't like mission critical for the lab. So after today, you'll be good to go on Lab 2. You got quite a bit of time though. The due date's November 10th. Although we might be able to get away with pushing it a little bit later if you guys need more time. So we left off last week building a custom linked list. The starting file that I'm using today was the same one that was posted in Blackboard at the end of last week's class. So if we go into week 6, I had posted that in-class demo where we were working with a linked list. I just downloaded it from there, and we're going to start again right from where we left off. So what we were working on in this file, let's just do a quick review of what's in here. We created a self-referential item class, and the item class is self-referential because it had a link to another item. So that means that each item has a reference to the item that comes after it. Now, in this example, we actually used it to make a doubly linked list, so we had a link to the previous item as well. But for my example today, we're going to just, I'm going to comment that out because I want to create it as just a single linear linked list. So I'm going to comment out any references to that previous pointer. Before we get started, I think that there are some in the other file as well. So I'm just going to build and find those. We'll comment them out, and then we'll move along with building our custom linked list. Take them all. Nope, not yet. We'll just comment those two, and then we're all set. Okay. So our custom link list class that we created, I inherited from iCollection, and iCollection here is type safe, so I've said that this is going to be a collection of item objects. So the most important parts of our list are the first pointer. Depending on what type of list you have, you might call it first, or if it's a stack, you would call it top, or you might call it head if you have a doubly linked list that has pointers to both head and tail. So you have this reference to the item that is the first one. Because every item contains a link to the one that comes after it, all you need is a link to the first one in order to get to all the rest of them. And we saw that last week in the demo where I kind of manually used the .next pointers to move from the first one all the way through the list by going .next, .next, .next over and over again. So we want to keep that reference to the first one, and we also want to keep it private because we don't want users to be able to directly modify that object. If you have a linked list of 200 items and you lose your connection to the first one, then all the other ones are going to be lost as well because there's no way to get through, from one to the next to the next. So we make sure that we keep that private. We don't allow direct assignment to that first element. In order for us to implement iCollection, when we implement this interface, it forces us to write all these different properties and methods. So we were kind of working our way through writing some of the properties and methods of iCollection, and we're going to look at the rest of them today. And then after that, I'm going to show you how to write an enumerator so that we can use a for each loop on our list. So that's what we've got coming up in today's slides. Before we move on to that, though, we're going to take a look at the item operator. So the item operator is something that is typically found in a list. You know, you first learned about this when you had an array. And we know that when we have an array, that you can access the array elements through this numeric indexer. So if you have the numeric indexer in a list, it allows you to pick out an element at a certain numbered position. Now our list right now is like a linked list chain where we would have something like this. Each object just points to the next one. But if we're trying to create something that treats this thing numerically, and I reference it and I say I want to access my list at position 2, that's this one right here, then all we would need to do behind the scenes is start at the first one and count. Okay, we're going to move up 1, 2, and then you would return that element. So we do that behind the scenes inside the item operator. So the item operator is these square brackets. And we're going to overload it so that we can control how a particular numbered item is returned. Now, because we're in charge of how the list works, we can make it work whatever way we want. You know, if we want to count from the end, or if we only want to count particular elements, or if we want to skip some or whatever, we have the control over doing that. Now, typically we wouldn't do anything unexpected like that because every other list and array works by counting from the first and counting up by 1. So it would be really kind of disconcerting to users if for some reason this weird list counts from the end instead of the start. But that being said, the point I'm trying to make is that you have total control over how it works. So we want to have control over where the new elements are inserted. I mentioned this earlier when you can't, or you shouldn't rather, allow direct assignment access to that pointer first. And this is the same sort of thing. I don't want to be able to assign a new element into any position that I want because the list that I'm making has a rule that all new items are inserted at the front. Last week when we created our add method, we're putting every new item that comes in at the beginning of the list. So if we've decided that that's a business rule for this particular type of list called custom list, it's a list where new items always go in at the front, then allowing assignment through the item operator would ruin that, because then if you don't want to put something in at the front, you could just assign it to, you know, my list at position 4. So we don't want to allow assignment. We want to make it read only, that you can read what element is at a given position, but you can't place an element into that position. What would happen if we had a list like this and I wanted to assign a new element at position 1? Well, I take my new element and I put it here, but this new one doesn't have a pointer to this element over here. So if I reassign that, I lose everything else as well. So it has to be a read-only operation. The only way that you can put something new into the list at this point in time is by calling that add method. So in order to write the item operator, we create it as a public property. So we have the data type public, and then, the access modifier public, and the data type is item. And then the name of the property is this with the square brackets, and inside there your integer index. So it's kind of you know, a funny way of looking at it when you think, well, what's the name of it? But the name of it is this with something like that. So this meaning this list at position 2. We're going to write a get but we're not going to write a set. So it's going to be read only. So whenever we reference some list at a particular integer position, then we have to write the code in here to return an item at that given index. So what kind of code do we need in order to do that? Well, let's get this started in here. The item operator isn't by default part of iCollection. All of these other properties in here, most of them we haven't implemented yet, they were all part of iCollection, but item isn't. So this is optional. You don't have to write the item operator if you're inheriting from iCollection. But if you're making a list, it's a nice thing to have. People appreciate being able to access things by a numeric index. Okay, so I'm going to put my property in here. Like that. And inside the get, we have to figure out, well, how are we going to return an item from the list at a given position? So if first is the one at position 0, first.next is at position 1, and first.next.next is at position 2, and so on and so forth. So all we have to do is start at the first one, and then go to .next I times. So if I is 0, we would go to .next 0 times, so we would still be at the first element. If I is 3, we'd go to .next 3 times, so we'd go first .next, and that would give us, the third element. So we have that ability to just move a certain number of times. So what we can do here is use a for loop to just move to .next X number of times. Now we also have to consider some of the edge cases. What are we going to do if the index is out of range? If we have 10 elements in our list and they want element 99, what's going to happen, right? When we try to go to .next, it's going to, break down. Or what happens if our list is empty, or what happens if they give us a negative index, or, we have all of those edge cases to deal with. And if any of those happen, then we're going to just return null. So we'll deal with that after. But for now, we're going to assume that I is a good index. I'm going to start at the beginning. And I'm going to use this current to talk about the current item that we're looking at. So before we do anything else, we're looking at the first element. And then I need to know how many times I'm going to go to .next. So I'm going to create a loop. Oh, I can't use I, we already used it. So I'll use J instead. So this loop will run I times. So if I is 0, it's going to run 0 times, which means we're going to not move to the .next. But if we want to move to the .next, oops, it'd be great if I could type the X. There we go. Then we can write something like this. So if I was 3, we would go current.next becomes current 3 times. Guys with me? Oh, good, okay. For a minute there, I was like, oh no, I've been talking to myself for a half an hour. All right, good, okay. Once we're done that loop, current is going to be sitting at the item at that particular index. So now all we have to do is say return it. Fairly straightforward, I think. Make sense? Okay, so now we have this to deal with. So let's think of all the ways that people can be jerks. Okay, so let's see. What happens if the I value, the index is negative? Well, we're going to return null there. Let's see, what else? What happens if our list is empty? So if our list is empty, that means that first won't point anywhere. Now, if our list is empty, do we have to have an edge case for that? What would happen if our list is empty? Well, we'd bypass this. Current would be null. We'd try to go to the next one if I is, greater. So it would break down here. Now, if I was 0, it would be okay because we'd skip over the for loop and we'd just return the null. But if I was 1 or anything higher than that, it would break when we tried to move to the next if our list was empty. So when we tried to go first.next, it would break. So we don't have to worry about when I equals 0. That will kind of work itself out. The problem is actually going to occur when I is greater than 0 and the count is not greater than 0. So this is really just another different kind of special case where we're looking for what happens if the index is higher than the number of elements. If the index is equal to the number of elements, then you're okay. But if the index is higher than the number of elements, then we got a problem when the index is 0. So the next edge case that we're going to look at is what happens if the I value is higher than the number of elements. Now, the number of elements, we're going to get this count property for that to tell us how many elements are in our collection. If we have 5 elements in our collection, the indexes will go from 0 to 4. So as long as, I is less than count, we're good. If it's greater than or equal to, that's a problem. So this should capture all the edge cases, including the list is empty one. Because if the list is empty, then the count is 0. And if I is greater than that, then that's caught by this. If I is equal to that, then that is also caught by this. And if I is less than that, it's caught by that. So I think we're all good. Now, count hasn't been implemented yet, but when we do implement it, then we'll be able to use it to determine whether we're going to return null if this is like the index out of bounds error. So all these parts are kind of going to work together. Now I believe my next slide is about the count property. Yeah, it is. So we're going to fix that part next. We can't test the item operator until we can test the count operator. So inside the get block, this is what we did. Iterate through our collection, counting the number of elements, return the element at that position. What happens if the list is empty? What happens if the index is out of bounds? So the index bounds are greater than or equal to 0 and less than the count, the number of elements, just like for any other list or array. So we need to implement count here. The count property returns the integer representing how many elements are in the collection at any given time. Here are some options on how to do this. There are other ways that you can do it, so this isn't like the hard and fast law of this is how you must do. So there's a few different options. One of them is keep an internal counter going. If you have like a private count variable, don't want to make that public, obviously. It wouldn't make sense to manipulate the count externally. But if we have a count variable like that, then we would need to make sure that when we add a new item, increment the count. And when we clear the list, reset. And if we have any like remove method, remove would need to say count minus minus, only if the element was found and actually removed though. So we would need to worry about keeping that maintained in various places. And then that makes this property really easy. All you would have to do is this. It returns that internal counter. So that's one way of performing that problem. Now I'm going to undo that so that I can show you the other way. Heading controls to add a bunch of times. Boy, I made a lot of typos there. Here we go. So let's get rid of that. That's one option. You can keep an internal counter. Just remember to increment it and decrement it when things get added and removed. The second option, in the count property itself, we can perform something similar to what we just did in the item operator, which just iterates through, moves to .next, and counts the number of elements dynamically on the fly. So depending on what the size of your list is going to be, if you have like 8 million items in your list, then number 2 probably isn't the way to go, because just doing the loop would take up valuable time and power. But for shorter lists, this is a little bit easier just because of the less coding that you have to do, as far as remembering to update something in like 4 or 5 different places. So I'm going to do that option there with the number 2. My count property, instead of an expression body, I'm going to write this. And again, it's got to be read-only. We don't want to be able to modify the count. So we're going to find out how many elements are in the list. I'm going to start at the beginning. And I'm going to do a while loop to count up a counter that starts at 0. So our while loop needs to iterate through the entire list. We're going to start at the first one, we're going to move to the next one, and then we're going to count as well. Here's the count. We're going to continue going until we get to the end of the list. Well, if we're moving current.next every time, the end of the list is going to happen when current is null. So I'm going to continue as long as current is not null. Move to the next one every time. So if the list is empty, current would be null because first would be null. So we'd skip the while loop and we'd stick with c equals 0. If the list has 3 elements in it, we would start at the first one. C would get incremented to 1, then we move to the second one. C would get incremented to 2, move to the third one. C would get incremented to 3. We try to move to the fourth one, but the fourth one would be null, so we'd be done. Looks good. And return our counter when we're done. Make sense? Okay. Somebody stop me if you need extra clarification. Otherwise, I'm just going to keep on going. We're going to move down to remove. So we want to remove an element from the list. With remove, you're given an item to compare. We've done this before. You did it on the test where our object implemented IEquatable so that we could write an equals method that allows us to specify what it means to match, what defines equality between items. Because if we don't specify, it will only match if it's literally the exact same object at the same memory address. So we're not, most of the time with lists, when we're searching for something to remove, we don't have the whole picture of the element. Because if we look at what the element contains, we might know the letter and the color, but not only do we need to know the letter and the color, but we need to have a reference to the item that's after it. If we wanted to do an exact match, right? It would match all the properties. So we can't just say we're looking for element A. We'd have to say we're looking for element A that's red that has B following it. Okay, well then what's B? Okay, well B is blue and it has C following it, and we end up not being able to do a proper match without knowing about the whole entire list. So that's why we write IEquatable with equals. We say in order for it to be considered equal, we're going to say if the letters match, why are there brackets here? If the letters match, then that's considered an equal element. So if I want to remove an item, all I need is an item with a matching letter. I don't have to worry about what the back color of the item. I don't have to worry about the item that comes after it. I'm looking for an item. Oh, I'm getting interrupted by a call here. I'm looking for an item that just has the same letter as the one that we want to remove. So when I call remove, I can create like a dummy item that just has a letter in it and no back color and no next pointer, and it will still match. Make sense? Anybody still awake? Okay, good. All right, all right. So let's get in here and look at our remove method. We remove the throwing of the exception. The item that comes in here, we're going to move through the list and find a matching item. Now we have a couple of different cases here. Remove can be tough because when we remove, and this is one of those times where I really kind of wish I had a whiteboard. Let me bring up the slides again. I can just use this area. When we want to remove, once we've determined what a matching item is, and we're going to iterate through the list to find that matching item. Does item work only with bool? Item is my object class. So my item class here has three properties: char, string, and another item. So it doesn't have a bool property. Oh, what's other? This case, when you call equals, it passes a reference to a different item because you want to compare them against each other. So this means like this current instance of the item, and then other as the parameter is the one that we're comparing it against. So what my line here says that if this item's letter is the same as the one we're comparing, then we would return true, saying that yes, they are equal. Yes, the equals method always just returns bool. It's a true or false. They're equal or they're not. problem. So we need to iterate through our list looking for an item that matches. And when we want to remove an element, we have to reset the pointers to go around it. And we have to make sure we do it in the right order so that we don't break the chain. So if we have a list like this, and we've determined that this is the one that we want to remove, in order to remove it, I have to make, let's see here, we'll make this one T and we'll make that one X. And we want to remove V. So if we want to remove V, essentially what I need to do is make T point to X. So that would be the step one, is making T point to X. But the problem here is that I need to make sure I don't lose my connection while I'm readjusting the pointers. So if I have found V and I'm pointing at current being V, in order to reassign it, I need to backtrack my way back to T in order to change T's pointer to point to X. And at the beginning of today's class, I removed the way to backtrack, right? So what I need to do is I need to make sure that I don't move ahead too far. So I'm going to erase that. Where's the eraser? And instead of looking for a current matching element, I'm going to stay back a step. And I'm going to look at current.next always instead. So if I've gone here and I determine that this one isn't a match, and then I move to the next one, and this one isn't a match, and I move to the next one, if this one's the match, now I'm stuck because I have to go back to T. So I have to do it the other way, where I'm going to start and look at the next one always and see if the next is a match. So when T is current, I'm going to see if current.next is the matching element. And if current.next is the matching element, that's the one I want to remove, then I can reassign current.next to go to X. So if I'm always comparing the next element, that's going to work for all cases except one. What happens when the first one is the one that I'm looking for? So if I want to match A, if I start at A, but I'm always looking at current.next, then I never actually look at A. So A is an edge case when the first element is the match. So we're going to check first, and then we're going to check first.next. And if neither of those match, then we're going to move to here. And then we're going to check the .next. And if it doesn't match, then we're going to move to here. And we're going to check. So that's two possible different cases. Either the first one in the list matches, and if that's great, then that's easy to remove because it's easy to remove the first element. All you have to do is assign first to this one. So that's easy to fix. Otherwise, we're going to have to start our look ahead program so that we don't move too far away. All right, so let's get some code in here to mean that we have two possibilities. The first one is the item we're looking for is first, or the item we're looking for is after the current one. So let's look at the first one first. You know, there's a third possibility where this thing isn't in the list at all. We'll deal with that later. So the first one I'm going to look at is if the item that's this guy here, the one that we're trying to match, exists as the first element of our list. So let's say, for example, we have a list like this, A, B, C, D. If we're trying to match A, we would remove A by making B first element. And we can do this either way because it's a measure of equality. So we might say if item dot equals first as well, either side, right? A equals B, B equals A, transitive. All right, so if that's the case, and I'm calling on equals here in my item class, if that's the case, then we're going to make B the first one by reassigning our first pointer to first.next. So first right now is A, first.next is B. We're assigning B by saying first equals B. Remove returns a Boolean data type. True if you were able to remove that item. So by doing this, we've removed an item. We return true. Now, if that's not the case, if A is not the element that we're looking for, now we've got to start looking at the rest of the list. So if we want to, say, remove B, C, or D. It's just a small example. So, keep in mind there could be a billion elements in this list. Maybe not that many. It depends how big they are. So if it's not the first one, then we have to start moving through. And we've already done it twice in today's class, moving through the list using either a while loop or in this case, we used a while loop as well, or we can use a for loop. Now, I'm not going to use a for loop because then I have to call on count. It's a little bit easier just to move and continue moving until you get to the end of the list. So we're going to start at the first one. Oops. And we're going to run our while loop. Same structure as I used last time. So what are the possibilities? The current one, right now we're sitting at first. We already checked first. We want to check next. We want to check B. So one option is we're going to check current.next for a match. The other option is what happens if we're sitting at D and we're trying to check current.next, but current.next is null. Let's go back to my little drawing here. What if I'm trying to match Z? Now I don't have a Z in this little example. So I'd say, does first match? Nope. Okay, does first.next match? Nope. Okay, we're going to go current equals current.next. That's our moving through. Does t.next match? Nope. Okay, we're going to move. Does v.next match? Nope. Now when we get to does x.next match? x.next is null. So we're checking something that doesn't even exist. So if we get to a point where we're trying to check something that doesn't exist, it means we've made it all the way to the end of the list and we didn't find a match. So if we made it all the way to the end of the list and we didn't find a match, we're going to return false. Remember that remove returns a Boolean. True if you found a match, false if you didn't. So I'm going to look at that first and say if, oh, excuse me, sorry, I do have to get that. Just give me 1 minute. Okay, sorry about that. So I'm going to finish this loop up, and then we'll take our 10-minute break. So if current, let's see here, if current.next was null, then we're going to return false. Otherwise, we're going to check current.next to see if it matches our existing item that we're looking for. And we're going to say if current.next equals our item. If that's the case, we need to skip over it. Just like we did up here, we want to reassign. So how can we reassign? If we're sitting at current and we want to reassign so that current.next points to current.next.next. I know it's a bit funny. There we go. So that will allow us to skip over the equal item, and then we can return true. If neither of these if statements happened, so current.next wasn't null, but it also wasn't the item that we're looking for. Let me just move this comment to where it belongs. The only other thing we need to do is say, okay, well, this one wasn't empty and it wasn't the one we're looking for, so we're going to move to the next one. So this will remove matching items. It will return true if we've matched. It will return false if we made it to the end of the list. And if we make it down here somehow, it's not really possible to make it down here, but this thing is also, telling me that the one final edge case that we actually didn't catch, if first is null, is the only way that we can get past all of this, because it wouldn't equal the item, and the while loop would be skipped over as well. So if first is null, it means the list is empty. If the list is empty, we can't match anything, so we return false. Okay, so that's the end of our remove method. Now, we'll take our 10-minute break since we're about halfway through, and then when we come back, we're going to look at the rest of the slides, so enumerators, and finishing up our list class by implementing those two left over. If we have time, we'll look at copy too, but I want to make sure we get through enumerators first.